So another common kind of series that we're going to see from time to time will be the telescoping series. To generate a telescoping series, this generally is going to involve the same function or same kind of function appearing twice, but as a difference of two different iterations of that function. So for example, if we had something of the form f of n minus f of n plus 1, what I'd like to do is just take a look at a couple of the partial sums that we could generate from this. So S1 would be f of 1 minus f of 2. To generate S2, we would be plugging in, taking the previous sum and then adding what we get when we plug in 2. So for n equals 1, we'd have f of 1 minus f of 2. And then plugging in n equals 2, this would be f of 2 minus f of 3. Now the idea is, for this telescoping series, a couple of these terms could cancel each other out, and we'd be left with f of 1 minus f of 3. For S sub 3, we'd be looking at the previous sum plus what we get when we plug in the current value of n. So that would be plus f of 3 minus f of 4. So what typically happens with these telescoping series is you wind up with a first term that doesn't cancel out, and a second term which cancels with the first term of what you're about to create. We'll do one more iteration of this so that we can see it happen one more time. So take the previous sum and add what we get when we plug in n equals 4. So this will be f of 4 minus f of 5. Now once you get to about here, it becomes a little bit easier to see what the generalization of this would be if we wanted to consider what the nth partial sum looks like. Now when we did S sub 2, the thing left over was f of 3. For S sub 3, we had f of 4. S sub 4, we had f of 5. So for S sub n, we're going to count on seeing f of n plus 1. Now typically what will happen is, in order to consider whether the series converges or diverges, we will need to consider the limit as n approaches infinity of this nth partial sum. So limit as n goes to infinity of f of 1 minus f of n plus 1. So generally the rule is that if this limit as n approaches infinity of this, if this is finite, the series converges. Now because it is a limit at infinity, typically what we'll see out of this is something that goes to 0. Not necessarily the case though. Now, it's going to be pretty infrequent that you are started off with something like this. Rather, you'll need to perform algebraic manipulations to get it into that sort of form. So, let's consider a couple of examples. First example that I'd like to consider is going to be the sum from n equals 0 to infinity of 7 over n squared plus 3n plus 2. In its current form, it definitely does not look like a telescoping series, but we are going to perform algebraic manipulations to turn it into that. Now this 7 over n squared plus 3n plus 2 is a rational expression. With this rational expression, I notice that I can factor the denominator. Denominator factors quite nicely into n plus 1 and n plus 2. However, we're supposed to see this as a difference of functions, and if I want to take one single fraction and express it as a sum or difference of fractions, that is going to involve doing a partial fraction decomposition. Partial fraction decomposition. So that's exactly what I'm going to do. First, I'm going to multiply both sides by our lowest common denominator, which is n plus 1 times n plus 2. So a will cancel out the n plus 1, and we'll be left with n plus 2. And for b, we'll cancel out the n plus 2 and have an n plus 1 left over. This is supposed to be true for all n, so I'm going to plug in n equals -1. That'll give me 7 is equal to a times -1 plus 2, and b times -1 plus 1. Leads me to the fact that a is 7. If I plug in n equals -2, I'll get that 7 is equal to a times -2 plus 2, that's 0, and b times -2 plus 1. A little bit of algebra lets me know that that means that b is going to be equal to -7. Now this tells me that the original series that we had is now expressible in the following fashion. This will be the sum from n equals 0 to infinity of a over n plus 1 plus b over n plus 2. Now to help emphasize that this is a telescoping series, I'm going to write out the first few terms and we'll see what happens. So this will be 7 over 0 plus 1 minus 7 halves. It'll be for n equals 0. Plus, for n equals 1, we'll have 7 halves minus 7 thirds. Plus, for n equals 2, that'll be 7 thirds minus 7 fourths. And for n equals 3, this will be plus 7 fourths minus 7 fifths. So what tends to happen is the second term that we get cancels with the first term of the next value of n, and we see the 7 thirds will cancel, the 7 fourths will cancel. Basically, everything will cancel with something later on. Now, if I wanted to generalize this, similar to what we did on the previous page, this is the limit as n goes to infinity of, we'll still have this 7 left over, and the thing that we'll be subtracting, at n equals 3, we had 7 over 5. That came from this term right here, the 7 over n plus 2. So this will be the sum of the series. Now with that in mind, as n goes to infinity, 7 over n plus 2 is going to go to 0. We wind up getting 7. So we can draw the conclusion the series converges to 7. Let's try out one more example of a telescoping series. For this one, we'll do the summation. N equals 1 to infinity of the natural log of 1 plus 1 over n. Now again, in its current form, it doesn't necessarily seem like it's going to be a telescoping series. In fact, if we were to start plugging in values of n, at n equals 1, we'd have the natural log of 1 plus 1 over 1. That's the natural log of 2. Plus, if we plug in n equals 2, this will be a half plus 1. That'll be 3 halves. When we plug in n equals 3, this will be 1/3 plus 1 is 4/3. You know, this really doesn't look all that telescoping in its current form. So here are some algebraic manipulations that we're going to do to it. First thing I'd like to do is express this as one single fraction. Lowest common denominator is n, so this will be n over n plus 1 over n. N over n plus 1 over n will be n plus 1 over n. Then there is a property of logarithms. The property of logarithms states that if you have the natural log of a quotient, you can split it into the natural log of, the difference of two natural logs. Expressed in this fashion, it's going to be a lot easier to see why this is a telescoping series. So at n equals 1, we would have the natural log of 2 minus the natural log of 1, plus at n equals 2, we would have the natural log of 3 minus the natural log of 2. At n equals 3, we would have the natural log of 4 minus the natural log of 3. And we'll do one more. This will be the natural log of 5 minus the natural log of 4, and so forth and so on. So if we're looking for the things that cancel out here, I see a natural log of 2 minus a natural log of 2. Those cancel. I see a natural log of 3 minus natural log of 3. Those cancel. I see a natural log of 4 minus the natural log of 4. Those cancel. So it looks like from the first term, what we're not getting to cancel out is the negative natural log of 1. And the thing that's not canceling out from the last term is the natural log of n plus 1. In order to determine whether this series converges or diverges, I need the limit as n goes to infinity of this. Now that's going to be the limit as n goes to infinity of the natural log of 1 is 0, so we don't need to keep writing that. So this will be the limit as n goes to infinity of the natural log of n plus 1. As its argument goes to infinity, the natural log tends toward infinity as well. It is for this purpose that you are allowed to draw the conclusion: this series diverges. So when it comes to telescoping series, you do need to check to make sure that whatever term you have left over that doesn't cancel out does wind up being something that does actually give you a finite value.